All right, let's just dive right into it. Today, in this explainer, we're tackling a fascinating paradox, one where everything you thought you knew about missing data and accuracy might actually be completely backwards. Seriously. We've all been taught that accuracy is the holy grail, right? But what if I told you that striving for perfect accuracy is actually ruining your data?
So I want you to keep this one specific question in the back of your mind as we go. Why does making your data messier actually make it more accurate? I know, it defies basic logic. We usually treat noise as the ultimate enemy of good science. But as we're going to see from some pretty incredible research on imputation methods, which is really just how we fill in missing data, sometimes injecting a little bit of chaos is literally the only way to find the truth.
Here is our roadmap for today. We're going to cover 1. The missing data dilemma, 2. Basic solutions in R, 3. The accuracy trap, 4. The power of noise, and finally, 5. Better tools for data. Let's get right to it.
Section 1, the missing data dilemma. This is a universal struggle, whether you are in healthcare, finance, or the social sciences.
You look at foundational statistics curriculums, like this BS statistics program at GCU Faisalabad, and they really hammer this home right out of the gate. Literally, semester 1, students are wrestling with data collection and measurement errors. It's a day 1 problem. But here's the kicker. The most common real-world fixes that programmers use to handle this missing information, they are deeply, deeply flawed. Which brings us to section 2, basic solutions in R. You know, it's wild how quickly we resort to simple data deletion when we first start coding. If you use R, you're probably super familiar with these quick fixes to purge or bypass missing info. You've got is.na to find the blanks, or the na.rm parameter to just casually skip over them during your math. But the real heavy lifter, and honestly the most dangerous one, is na.omit. It just ruthlessly strips out any row containing a missing value. Sure, it's the absolute fastest way to clean a dataset, but it comes at a massive potential cost. The problem is, simply dropping rows relies on a massive, sweeping assumption that those missing records aren't uniquely important. Think about it. If you're running a medical study, what if the patients who dropped out, and therefore have missing data, are the exact same ones who suffered severe side effects? By just hitting delete, you've completely skewed your entire analysis. It's incredibly risky. So, moving to section 3, the accuracy trap. If deletion is bad, we should just predict those missing values as perfectly as possible, right? Fill in the blanks with our absolute best guess. Well, actually, no. Welcome to the accuracy trap. Minimizing mean squared error, or MSE, feels like the holy grail of machine learning, and the logic seems flawless. If you have to guess a missing value, you obviously want that guess to be as close to the true value as mathematically possible. You want zero error. But optimizing for this specific accuracy metric is basically a mathematical trap when you're dealing with missing data. Here's the crucial contrast. On one hand, you have the predict method. It tries to be absolutely perfect. It uses regression to find the exact conditional mean and minimizes that MSE. It is highly deterministic. But then you have the draw method, which does something totally radical. It looks at the missing data, acknowledges the inherent uncertainty, and purposely injects stochastic noise, literally random noise, into the prediction to capture the natural, messy distribution of the real world. Now, you might be thinking, why on earth would we ever want to add noise? Well, because the hidden costs of the predict method are brutal. By generating these perfect expected values, predictive imputation over-smooths your data. It absolutely destroys natural variability. Since every guess is placed flawlessly on a regression line, your dataset's overall variance gets artificially dragged downward. Meanwhile, your correlations and your R-squared values shoot through the roof because everything looks perfectly aligned. You end up with overconfident, heavily biased estimates that completely ignore the reality of uncertainty. That leads us right into section 4, the power of noise. Let's look at how this builds into our central paradox and how we actually fix this over-smoothing problem. The solution to this accuracy trap is brilliant. You have to purposefully introduce random error. Specifically, the research shows you need to match the noise level to the residual variance of your imputation model. It's like you're telling your algorithm, look, don't just give me the perfect sterile average. Give me the average, but then scramble it just a tiny bit to mimic the actual messy real world. When you run the numbers through a simulation, the paradox is glaring. The ground truth, the real, untouched data, has a variance of 1.15 and a correlation of 0.87. Now check out the predict method. It shrinks that variance down to 1.10 and spikes the correlation up to 0.91. It makes the relationships look way stronger than they actually are. But the draw method? By adding that random noise, it perfectly preserves the true data relationships, giving us an incredibly accurate variance in correlation.
But here is the craziest part. Look at the MSE. The draw method actually doubles the mean squared error compared to the predict method. It is technically twice as inaccurate on a single point-by-point basis, yet it's vastly superior for maintaining the integrity of the whole dataset. This proves exactly why using MSE as your sole judge for imputation quality is a terrible idea. It prioritizes individual point accuracy over the actual variability of the entire population.
All right, final stretch, Section 5, better tools for data. How do we actually apply this theory to our everyday workflows?
Because this isn't just theoretical, it impacts the literal software packages data scientists use every day. Popular predictive tools, unfortunately, rely on that flawed MSE logic. MissForest optimizes a loss function, which systematically introduces bias and overfits to the conditional mean. SoftImpute can give you a highly unpredictable spread when your data signal is low. But then there's a package called MICE, which stands for multivariate imputation by chained equations. It adopts a Bayesian framework. It embraces the randomness. And because it's stochastic, it produces unbiased estimates that actually match our true population.
So let's turn this into some actionable steps. Next time you're tempted to just delete a row with missing data using na.omit, just pause, investigate it. Stop falling into the accuracy trap by treating imputation as just another MSE prediction problem. Instead, try utilizing stochastic tools like MICE to add proportional random noise back in. You have to marginalize downstream estimates to account for that uncertainty so your analysis doesn't end up lying to you with false, over-smoothed confidence. I want to leave you with a pretty provocative thought. When we strip away all the natural noise of the world just to make our mathematical models look cleaner and more precise, we might actually be drifting further away from the truth. So the next time you see a perfectly pristine statistical model in the news, ask yourself, has the messiness been preserved or has it been invisibly over-smoothed? Thanks for joining me on this explainer and keep questioning the data.